Deep inside your car's axle, there's this absolute mechanical marvel called the differential. And today, we're going to tear it apart, figuratively, of course, to see exactly how this incredible set of gears solves one of the most basic but tricky problems in driving: how to turn a corner without everything going haywire. All right, let's kick things off with a little brain teaser. Look at this setup. If that top gear starts spinning clockwise, which way is the bottom one going to turn? Now, your first instinct might be to say counterclockwise, right? But the real answer is, well, it depends. Seriously, it could go clockwise, counterclockwise, or not even move at all. It all comes down to the other forces at play. And that flexibility, that's the absolute secret sauce of the differential. Let's dig in and see why. Okay, so the problem with turning, or why a simple solid axle just won't cut it. So why do we even need this complicated-looking thing? Well, to really get why the solution is so brilliant, you first have to understand the problem it's solving. Picture this. You've got both of your car's drive wheels connected by one simple solid bar of metal. When you're driving in a straight line, no problem. But the second you try to make a turn, yeah, that's where it all falls apart. Think about it. When your car makes a turn, the wheel on the inside of the turn has a much shorter path to travel, right? But the wheel on the outside has to cover way more ground to keep up. So, to make that turn smoothly, the outer wheel absolutely has to spin faster than the inner one. And if they're both locked together on a solid axle, well, that's physically impossible. Something's got to give. And when that something gives, it's not pretty. Forcing both wheels to spin at the same speed means they literally start fighting each other. One of them is forced to slip and scrub across the pavement just to keep up. What does that mean for you? Well, you're going to shred your tires, for one. The car becomes a nightmare to handle in a turn. And all that fighting puts an incredible amount of stress on the axle itself, enough that it could literally just snap in half. Not good. So how did engineers solve this massive problem? Let's meet the hero of our story, the open differential. This is just such an elegant mechanical solution. It's a device that cleverly lets the wheels spin at totally different speeds, all while still getting power from the engine. So let's do this. Let's build one, piece by piece, to really see how it works. First things first, you've got power coming from the engine. It travels all the way down the drive shaft and connects to this guy right here, the pinion gear. It might look small, but it's absolutely crucial. Its only job is to take all that rotational power from the engine and get it into the differential system. Now, that small pinion gear meshes with this big fella, the ring gear. And the size difference here is super important. It's a classic gear reduction. It slows the rotation down, but massively multiplies the torque, that's the twisting force, which is what you need to actually move the car. The ring gear is bolted directly to the differential's case, so when the ring gear spins, the whole housing spins with it. Okay, now we get to the real magic. Tucked inside that spinning case, you'll find these smaller gears. We call them spider gears. And here's the trick. They get carried around in a big circle as the whole case rotates, but they can also spin on their own little axles. This ability to have a second spin, a rotation within a rotation, that is the absolute key to this whole thing. And finally, those spinning spider gears mesh with these two side gears. Each of these side gears is connected directly to an axle shaft, and each axle shaft goes out to one of the wheels. And that's it. We've built it. The power flows from the pinion to the ring gear, which spins the case, carrying the spider gears, which turn the side gears, and boom, power to the wheels. All right, gears in motion. Let's see how it all works together. Now that we've got our differential assembled, let's put it to the test. We're going to look at how this incredible collection of gears behaves in two key situations: driving straight ahead and then making a turn. Okay, scenario one, we're driving in a perfectly straight line. In this case, both wheels are spinning at the same speed, and they have the same amount of resistance from the road. Because everything is equal, those magic spider gears, they don't actually spin on their own axles. They just get carried along for the ride inside the case, and they push on both side gears with equal force. The whole thing basically locks up and acts like a simple solid axle. But now let's make a turn. This is where the genius of the design comes alive. Remember how the inner wheel needs to slow down? Well, as it slows, the resistance on that side goes up. That difference in force is what makes the spider gears wake up and start spinning on their own axes. And as they spin, they allow the outer wheel to speed up by the exact same amount that the inner wheel has slowed down. It's a perfectly balanced mechanical equation, all happening automatically. Okay, this all sounds perfect, right? A brilliant, simple solution. But this design has a major weakness. An Achilles heel. The very thing that makes it so clever on a nice, grippy road turns into a critical, immobilizing flaw the second you lose traction. It all boils down to a basic law of physics. Power, like water, follows the path of least resistance. The differential is designed to do exactly that. It sends the engine's power to whichever wheel is easier to spin. Now, during a turn, that's what we want. But what happens when the path of least resistance is a wheel that's just spinning freely with zero grip? So let's play this out. Picture it. One of your drive wheels is sitting on a sheet of pure ice, and the other one is on nice, dry pavement with tons of grip. Which wheel is easier to spin? The one on the ice, of course. So the open differential, doing its job perfectly, says, great, I'll send all the power over there. And what happens? That one wheel spins uselessly on the ice, while the wheel with all the grip gets nothing. In your car, it's completely stuck.
This exact problem, this one wheel on ice scenario, is the reason engineers had to go back to the drawing board. They needed a smarter differential. Their goal was to figure out a way to override that path of least resistance rule and actively force power to the wheel that can actually use it. This led to the next step in the evolution.
And here's the difference in a nutshell. The open differential sees a slippery wheel and sends all the power to it, leaving you stuck. But the limited slip differential, or LSD, is smart. It senses that one wheel is slipping and says, nope, that's not useful, and it actively limits the power going to that wheel and redirects it to the one with traction. The result? You get moving again. So how does an LSD do that? Well, a common way is by adding a set of clutch packs inside the differential. These clutches basically create a friction link between the two side gears. This friction makes it harder for one wheel to just spin up way faster than the other. It essentially forces some of that engine power to transfer across to the wheel that isn't slipping, the one that actually has some grip. So as you can see, it's really about picking the right tool for the job. You've got your basic open differential. It's cheap, it works great for just everyday driving, but its big weakness is any slippery surface. Then you step up to a limited slip, or LSD, perfect for performance driving or some light off-roading, but it's more complex and costs more. And then you have the big guns, a locking differential. This is for serious off-roading. It can lock the axles to a 50-50 split, but you absolutely cannot use it on dry pavement. It's all about trade-offs. So let's wrap this up. What are the big things to remember? First, differentials are absolutely essential. Without them, you just can't turn a corner properly. Second, the standard open differential is a brilliant solution to that turning problem, but it fails spectacularly the moment one wheel loses grip. That flaw led to the invention of limited slip and locking diffs, which are all about managing where the power goes. And finally, the type of diff in a car tells you a lot about what that car was designed to do. It's a huge part of its personality.
And that leaves us with one last big question for the future. As we move into an era of electric cars, some of which have individual motors for each wheel, do we even need these incredible mechanical marvels anymore? Think about it. This whole elegant physical dance of gears that we've just gone through could be completely replaced by software. Just lines of code telling each motor exactly how fast to spin. The job of the differential is still essential, but its beautiful mechanical form might just be on the verge of becoming a thing of the past.